Hi, in this lecture, we're going to introduce circuit analysis methods, including KVL, KCL, and some of the pretty critical and fundamental circuit analysis methods. For example, like the mesh current methods, node current methods, and supermesh and superposition, all these kind of things. So first of all, let's have an example of the simple circuit and see how KVL and KCL works. Here's an example of the circuit. Here's a voltage source, and got a resistor, another resistor, and one more resistor over here. This is 30 volts. This is voltage drop across this 8 ohms resistor is called V1. And the voltage drop over here is called V2, and this is the 3 ohms resistor. And here is a 6 ohms resistor, and voltage drop over here is called V3. And there are 3 currents. For example, that's a junction of the circuit, and we are going to call the current flow into the junction from the left side is I1, and flowing out to the right side is I3, and flowing down, that's I2. Okay. So the purpose for circuit analysis is to solve this linear circuit. So solve a circuit means you just want to get to know what are these unknown currents and voltages at every single place in the circuit. So for example, I labeled the current here like I1, I2, I3, but I don't know what's the value of this current actually, right? So what is this one? You don't know. I mean, you want to use Ohm's law probably, you know this is 30 volts. Kind of tricky because this resistor is being shared by these 2 circuits loops, so you couldn't directly apply Ohm's law to calculate I2. So at this point, if you want to solve every single current and voltage in the circuit, in this linear circuit, you do need these circuit analysis methods. So the first one, the first fundamental law you want to use is called KCL. So KCL stands for Kirchhoff's current law. And the second one is called KVL. It's Kirchhoff's voltage law. Okay, so let's look at the definition for each of them individually. And keep in mind, these 2 ones are the most important circuit laws you want to learn at the very beginning. If you understand these 2, all the following ones, the analysis methods will be way easier compared to if you don't know what are these 2 fundamental laws. Okay, so KCL, let's look at KCL first. So KCL is defined as the sum of all currents that enter an electrical circuit junction is 0. The sum of all currents that enter an electrical circuit junction is 0. So which means sigma, which is the sum, the symbol for summation, and these are all the currents, right? Just add them together. So these are all the currents entering a junction, and that equals to 0. Okay, so if I draw a junction here, I1, for example, that's 1 wire, has I1 here, and I2, and I3, I4, right? So all these four electrical currents are flowing inside the junction. So depends on the definition of the KCL, then you can get this, right? So it's I1 plus I2 plus I3 plus I4 should be 0. Okay, keep in mind, that's the definition of KCL. And there is an alternative way to describe this law in the same effect. I mean, eventually it's pretty much the same thing, but it's being described in a slightly different way. So, or you can say the sum of current enter a junction is equal to the sum of currents that leave the junction. So let's see why this is the same. So for example, we are looking at this one, right? So I1 plus I2 plus I3 plus I4 equals to 0. That's a law. Won't change at all. It's going to be always work. But for this description, it's saying the current enters this junction equals to the currents that leave the junction. So I3, I4, now they're leaving instead of entering the junction. So which means I1 plus I2 equals to I3 plus I4. I mean, these are pretty much the same. Why? If you look at the first one, apparently this equals to this. Right? You just move I3 and I4 to the right side of the equation. Okay? And if you look at the direction of the current, because the currents are vectors, and if you put a minus sign over here, that means it's flowing in the opposite direction compared to the original current. So I3, I4 right here are actually minus I3 and minus I4 in the first case. Okay, so I1 plus I2 equals to I3 plus I4, and now here I3, I4, if I put a prime here, for example, just trying to differentiate the two I3 and I4s. These two, I3 actually equals to minus I3, I3 prime equals to minus I3, and I4 prime equals to minus I4. So you can say if you plug in I3 minus I3 and minus I4 into this equation, you are getting I1 plus I2 equals to minus I3 plus minus I4. Right? If you compare, they are the same. So when you are looking at the circuit, you can do it in either way, because sometimes the currents are being labeled in a different direction. They are not necessarily like entering the junction all the time. So in these cases, you should know that you can use either of the descriptions to solve the circuit in a relatively faster way. So you don't have to give a minus sign and let the current get entering the junction all the time. Okay? Hopefully you can understand this. It's very important. And the second one, let's look at KVL. So KVL stands for Kirchhoff's voltage law, and it is defined as this, like the following. Okay. The sum of all voltages or potential differences in an electrical circuit loop is 0. the sum of all voltages or potential differences in an electrical circuit loop is 0. So which means if you have a sigma, then you just add all these voltage differences, you are getting 0, right? So let's look at the circuit. So I have a voltage source, I have a resistor, another resistor, and this is called R1, this is called R2, and that's V, right? And the potential drop is like this, plus minus, because the voltage here is higher than here, and we ground here. So we know that the current is going to flow in the circuit, and we call the current I, not I1, sorry. And the sum of all the voltages and potential differences in an electrical circuit loop is 0. So which means if you add all these voltage drops across the entire circuit or the loop, and the result should be 0. Okay, because the voltage here is V, and if we start from here, like, you know, you can draw a person. Just imagine like there's a person walking through the circuit, and you use the sign whenever the first sign you can see before you start across this component. That's the trick when you are doing KVL, and always work. So follow that direction. For example, a person is going to walk through this circuit, and the first time the component this guy bumped into is going to be this guy, and the sign here is minus, and the voltage is V. So you want to just write down minus V over here. And for here, that's a plus sign. For example, this person right now is here already, and it's a plus sign, and the voltage is IR. Because the current is I and the voltage is R, right? IR1, actually, this is R1. And then the other resistor, and it's a plus sign, and the voltage will be IR2. So these are all the voltage differences. You have to follow one direction. You cannot just go back and forth. It's one direction, and find out the voltage drops. So the voltage drops can be, negative, can be positive. Doesn't matter. You just write down the first sign this person is going to see. So here's minus plus plus, minus plus plus, and this equals to 0. And that's how you can solve it. If you move V over here to the other side of the equation, and you are getting V equals to IR1 plus IR2, and eventually you can solve I equals to V over R1 plus R2. Okay, so you can see you can use KVL to solve a pretty simple linear circuit. And after this, let's look at some of the examples, very simple examples about what are these applications for KVL and KCL. Just very simple examples. And in the following lectures, we are going to cover tons of examples so you can master these circuit analysis methods. Okay. So for a very typical application for KVL, is called mesh current method. Okay, you have voltage source over here, resistor like this, and this is 30 volts. This is 8 ohms. This is 3 ohms. This is 6 ohms. So you want to label, since it's a mesh current method, so you are going to label the mesh current first. And I'm going to label in this way. I1, I2. So keep in mind, the mesh current is not necessary to be the real current flows through every single component. So if I label a match current like this, I1 is the real current flows through this resistor, but not this one. Keep in mind, because we are looking at the total summation of the current flows through this guy, because this guy is being shared by these two meshes. You know what I mean? So I'm going to just directly write down the mesh current equations, and you'll get it pretty soon. No worries. So let's list the KVLs for each mesh. Okay, we start from here, and we are going to see this minus 30 volts first, and then we get into here is a plus minus because the current flow in that direction, so there will be a voltage drop according to Ohm's law, right? So it's going to be 8 times I1, and then get into here. That's one mesh. Let's finish the first mesh first. So I1 is flowing down, and I2 come back here is going up. So the entire effect, or the total effect for the current flow through this resistor, we can call it the effective current flow through this resistor, will be I1 minus I2, because I1 is going down, I2 is going up, and if we are going to label this as plus minus, you are actually looking at treating I1 as positive, right? So it's going to be I1 minus I2. That's effective current flows through this resistor, and this equals to 0 according to KVL. Okay, now let's try the second mesh. If we have a person start working from here in the second mesh, going up, and the first resistor this person is going to see will be the 3 ohm resistor. And since we are treating I2 is going up, I2 is positive, right? So we need to use I2 as a positive current. So it's going to be 3 ohms times I2 minus I1. Because I1 is going down, I2 is going up. And plus this guy. There's no I1, only I2, so just plus 6 times I2 equals to 0. And you have 2 variables and 2 equations, so you can definitely solve for I1 and I2 in this equation. Okay, I'm not going to show you how to solve this. It shouldn't be that difficult. Just do a substitution, and I'm pretty sure you are able to solve it pretty easily. So that's an example for KVL. What about KCL? So the very typical application for KCL is called the node current method. If we are using the same circuit, it's called node current method. And the same current, circuit, let's draw it here, a little bit smaller. The same circuit, 30 volts, 8 ohms, 3 ohms, 6 ohms. Because this is a node current, so I'm looking at the node over here, and here's one current flow into the node, and another one going out, and another one going out as well. It's called I2. Okay, so there are 3 currents because there are 3 wires connect to the junction. So 3 currents flowing in or flowing out from the junction. And so these currents are called node currents. Compared to the mesh current, it's different because the node current, they are exactly the current flow through that branch in the circuit. The mesh, not necessary. If there's nothing sharing, no other meshes sharing this resistor, then it is. But if the resistor is being shared by 2 meshes, then it's not. You have to find out the effective current eventually. But node current is different. They are exactly current flowing through every branch. Okay, and according to KCL, the currents flowing in into the junction equals to the currents flowing out from the junction. So you can list one equation instantly, right? So it's going to be I1 equals to, which is getting into the junction, equals to I2 plus I3, which are going out from this junction. And now you have 3 currents. I'm pretty sure you can list all these equations for every single branch in the circuit. And now here's the first question. What about the second question? Where can we get the second question? Because this point and the ground has the same voltage difference for these 2 branches. These 2 resistors are in parallel, right? I can label this as V0, whatever, but I'm not going to use this variable. It's just introducing more variables. But you should know that because I3 is flowing through here I3, I2 is flowing through here, and you know that 3 times I2, which is the voltage VO, equals to 6 times I3, which is also VO. Okay, that's the second question. Second equation. What about the third equation? 30, if we label this part as VO, then the voltage here and the voltage drop over here must have some relationship with VO. Okay. If we just look at the first part over here, and this is VO, this is also VO, you can use the bigger circuit here, or you can use the smaller circuit here. Doesn't matter. And if we just look at the smaller one, and if you start from here, then it's going to be minus 30 volts. It's you know, in the node current method, you are using KCL for some of the equations, but also you can use KVL for the very last equation. Doesn't matter, as long as you can solve the circuit. So now we need to find out the relationship between the 30 volts and all the currents, since we haven't used the 30 volts by far. Okay, so minus 30 volts, a person start walking through the circuit, and then plus 8 times I1, and going down here, it's going to be I2. So you need this equals to 0. Okay, you must be wondering how this can work. I mean, no worries about why here, when you are involving 30 volts and I1, I2 in this mesh, why do we have to use this? But why here you are doing this, right? It's kind of interesting because I1, I2 are not the same I1, I2 over here. These I1, I2 here do not equal to the I1 and I2 over here. They are different. So that's why you are allowed to list this equation. And you combine these 3 equations, you should be able to solve for I1, I2, I3, since 3 equations, 3 variables. Okay. So in the following lectures, I'm going to cover more examples, and I will solve all these linear equations instead of just throwing the equations out here and without solving them. Okay. We'll see you in the next lecture.